We're moving on to momentum and collisions and impulse and things like that now. We'll start with the idea of impulse. Impulse is going to equal a change in momentum. And we give the letter P for momentum. Momentum equals mass times velocity. Okay, so we have two billiard balls and they're about to collide. We're going to do a force versus time graph. Okay, and initially there's this is 0 here for our force. We have no force, and all of a sudden a quick collision, and then up with the force, and then down, and no force after the collision has occurred. So our impulse occurs when the two balls are in contact with each other, which is for a very, very brief time. So this is when they start colliding, and then when they stop the collision, and then they're back to no force. Okay, the total impulse then would be the area under this curve. Okay, which impulse then is equal to force times time. And let's see how that works. Well, force is mass times acceleration, so we have kilogram meter per second squared, and we multiply that by a time, and we see that second squared crosses off with a second, and we're left with kilogram meter per second, okay, which is what mass times velocity is. So impulse is equal to force times time, which also equals the change in momentum. So we do mass times v2 minus v1. So how does that work? Well, we have a force between these two balls here. We can look at the impulse on this ball here. So we can take the mass of this object and multiply it by the velocity after the collision, which is probably going this way after it collides. So that's kind of v2, and this one's v1. So we take the mass of this object multiplied by v2 minus v1, and we'll calculate the impulse on this. And then we can do likewise with this one. Here's our v1 for this one, and then v2 we expect to be going backwards here. So there's v2, or maybe not backwards, depending on what's really going on here. So, but most probably backwards. So we can take the mass times this ball times v2 minus v1 to get impulse. That's also equal to force times time. So if we know the time of collision, I can find force by taking impulse divided by time. So as long as I know the time of collision, I can then find the actual force of the collision. And of course, the time of collision might be a couple tenths of a second here, or maybe a little bit less than that. And then we can get the force, okay, of that collision. But please notice you calculate the impulse on individual objects. So I can calculate the impulse of the 9 ball here, or the 11 ball, but they would indeed be equal to each other and opposite. So whatever force that the 9 ball receives, that'll equal an opposite to the force that the 11 ball receives. Likewise, whatever change in momentum or impulse the 9 receives, 11 receives the same but opposite. Okay, now let's look at our equation. Force times time is equal to mass times velocity 2 minus velocity 1. So impulse equals force times time. So if I have two collisions and each of them have the same impulse, so we're going to leave this as constant. If we increase the time of collision, then that would mean the force would have to decrease. And likewise, if we decrease the time of collision, and again impulse stays the same, then the force must increase. So we see lots of applications in collisions for cars. Today cars are designed to kind of become more like accordions when they collide, and when that happens, the force of the collision goes down because the actual time of collision goes up as the cars become more like accordions. Long distance jumpers and short distance jumpers do the same thing. They may bend their knees when they collide with the ground, and it increases the time of collision, therefore the force of the collision actually becomes less. Now there are two kinds of collisions we can talk about. One is an inelastic. Inelastic collision is when kinetic energy, okay, is not conserved, so it does not equal a constant. So what that means is the kinetic energy before the collision does not equal the kinetic energy after the collision. And you can also think of an inelastic collision as when two objects collide and stick together. So let's take a look at these two cars here. We've got velocity 1 here for this mass, and then we have velocity 1 for this mass here. After they collide together, the two come together, and the velocity decreases. So inelastic collision has a general form of something like this. So m1 v1 plus m2 v1, and these two v1s don't have to be the same, equals m1 plus m2 times some common v final. Okay, and so the important thing to remember that momentum, and again p is what we use for momentum, okay, is equal to a constant. In other words, and I'll put summation symbols here, the sum of kinetic energy before a collision and after the collision is not constant, but the sum of momentums before the collision and after the collision, that has to be a constant. So there is no loss of momentum, but there is a loss of kinetic energy. Now please remember that we are not losing kinetic energy, we're actually converting kinetic energy into the internal energy of the system as the two masses, come together. So again, it's just a conversion from one kind of energy into another. Now the second collision that we have is actually an elastic collision. So if we have two billiard balls, they are colliding and they bounce, and then they are separate afterwards, so they don't stick together. So the sum of kinetic energy for an elastic collision does equal a constant. So what that means is the kinetic energy before the collision must equal afterwards, and the sum of momentums is also a constant. So what that means, the sum of momentum before the collision, must equal the sum of momentum after the collision. Okay, and so in all collisions, momentum is always conserved, but kinetic energy is only conserved in elastic. So this has a general form of something like this. So we'll say M, A, and we'll just use symbols VA, okay, plus MB, VB, and that's simply the initial conditions there, is equal to MA, V final, and I'll give that sub A there, plus MB, V final sub B. Okay, so what that means is the velocity before the collision is VA for this ball, and before the collision is VB for this ball. After they collide, both of them are moving separately afterwards, so really you get two unknowns. So you do have to do a sum of kinetic energy. So I'm going to do 1/2 MA VA squared plus 1/2 MB VB squared equals 1/2 MA V final A squared plus 1/2 MB V final B squared. So we can use these systems of equations to find the two unknown velocities here, because we'll have two unknown velocities and we need two equations to actually solve them. So that's how you deal with momentum, impulse, and the two kinds of collisions. In our next video, we'll look at some special cases. Hey.